So now we're going to look at what you have to do in order to calculate these K values. And there's this method that I always like to use, and it's called the ICE chart. So that's what I'm going to do right now. I'm going to show you how to use an ICE chart. And if you look anywhere on the internet, you'll find plenty of examples on how to solve equilibrium problems using ICE charts. It's kind of like a nice methodical way of always being able to get to the answer. So here's my example. So my example is this. I'm given the initial concentration of N2O4. Here's my equation that I'm going to be using, that same simple one I started with. N2O4 decomposes into 2NO2, and then it reverses right back around to form N2O4 again. And it continues in this way until the rates are equal. When the rates are equal, they establish concentrations that will set themselves up according to the expression that we talked about. So if I'm given the initial concentration of N2O4 as 0.02 molar, you have to be careful. Sometimes it will be given as moles per liter. So 0.02 moles for every 1 liter. It might say 0.02 moles are in a 1 liter vessel. If it's at something like it were, 0.02 moles is in a 2 liter vessel, then you just have to be careful because your concentration would be 0.01. So you just want to watch for that. So at equilibrium, I know this is a given. This is an important piece given. At equilibrium, I know that once the reaction has achieved its equal rates, forward and reverse, there's an equilibrium concentration of the NO2 of 0.031. So here's how I set up the ICE chart. The information that I'm given in my problem is this. I have 0.02 moles of the N2O4, and I call that my initial. This is my initial row. I have 0 of the NO2, but I do know the information given that I have this much NO2 at equilibrium. Okay, so there's my information given in my problem. 0.02 of the N2O4 and 0.031 of the NO2. So now I look at what I like to call this little simple algebraic equation that's given through this information here. I have 0 to start. It's going to change by 2x, and I'm going to end up with this. Well, how do I know it changes by 2x? I know that as the reaction progresses, this original product's going to go down by x. If this goes down by x, the product here has to go up by x. The reactant here goes down by x, product goes up by 2x. Where do I get that x and that 2x from? Well, here's my coefficient 2, which is where this 2 comes from. And then I have no coefficient here, so I know that this is just going to go down by some variable x. So what I know is that 0 plus 2x, I should probably get that out of there because it looks like it's a minus. So I'm going to say 0 plus 2x equals 0.0310. And so how do I solve for x? I divide both sides by 2. I come up with a value of x of 0.0155. So now I go here and I take 0.02 minus 0.0155. So this value here is the one that I solved for in this little algebraic equation that I did. And I know that 0.02 minus 0.0155 is equal to 0.0045. So when I do this, I now know what my equilibrium concentrations are. I know that the N2O4 is 0.0045. This one was originally given. Now I just plug it into the expression because the expression is the concentration of NO2, my species that's on the product side, squared because of the coefficient 2 divided by the concentration that I have now solved for, that the N2O4 is at equilibrium. I do the algebra, I divide it out, I come out with a 0.214 concentration, equilibrium constant for my Kc value. So then the other piece down here simply shows how to achieve equilibrium starting from the other side. So if I took this reaction and I started initially, right, so this is my ice chart again. This is initial, this row is change, this row is the equilibrium. If I start out with 0.03 moles per 1 liter of the NO2, now it's going to go back, it's going to start out in this direction. So this is the side that's going to go down by 2x. This would be a given in the problem. And so what I know is that 0.03 minus 2x is equal to that given information in the problem. And then once I can solve for my x is 0.00285, then I can say 0 plus x is equal to that. Because my x is the 0.00285, I know what that value is. So now I take these values, and even though I started on the right-hand side, I should be able to calculate it out using the same expression, which is the NO2 squared. So this is the expression I used in both examples, NO2 squared over the N2O4. And I should get the same value. When I did it out, I came out with 0.207 here, 0.214 here. It's really, the difference is really due to any sig figs that I wasn't necessarily paying attention to. So, I don't think you're going to have to worry about the sig fig piece because I typically tell you what you need to worry about for sig figs. So I hope that helps. I'm going to stop there.